So the first thing that we are going to be talking about is a couple of very important functions. You may be familiar with them from your prior classes and all of that kind of stuff. You may not be. It just kind of depends on where you're at in your math sequence and all that kind of jazz. So the first function that we're going to talk about that is critically important to what we're doing is what's called the unit step function. And this has another name that you may have heard, the Heaviside step function. So mathematically, our unit step function u of t will be defined for our purposes as having a value of 1 for all time greater than or equal to 0, and a value of 0 for all time less than 0. So if I were to plot my Heaviside step function, it might look something like this. So here's my time axis. This will be 1 unit tall, so it would be 0 all the way up until t is equal to 0, instantaneously jump up to a value of 1 at t is equal to 0, and then it stays 1 forever. Okay. So this function mathematically describes kind of how we've been implementing switches in our circuit, because this function effectively just turns something on, right? So if I had a voltage source that was, let's say, 5 u of t volts connected to some electrical network, this is just a slightly different way to interpret the following switch system, where we might have a short circuit here, a 5-volt source here, and then a switch. So here's my contacts up here. So we would start at this position and switch over to this position at some time t is equal to 0. And then there's the remainder of our circuit. So we're just mathematically describing effectively the way that a switch works so that we don't, there's no potential for ambiguity or anything like that. So at all time before t is equal to 0, the voltage source is off. Abruptly at t is equal to 0, our voltage source turns on and it supplies exactly 5 volts to our circuit. So the unit step function, because it is a mathematical function, can be shifted in time, right? So if I had u of t minus 3, that might look something like this. So if this is t is equal to 0, this point in time is t is equal to 3. And this vertical axis here corresponds to 1. Then our signal would be 0 until we hit t is equal to 3. It would abruptly shift up to have a value of 1, and then it would stay 1 for all values of time greater than 3. If we flipped the order of these things such that we had u of 3 minus t, that is effectively the same thing as flipping this signal around this axis at t is equal to 3, so that we would have something that looks like this. So here's 0, here's 3, this is 1, so it would be high until we hit t is equal to 3, and then it would turn off. Okay. I'm bringing this up particularly because we're going to use this concept of a inverted unit step function, or one that's working backwards in time when we get to some of our integrals and all of that kind of stuff later. Okay. So this is our unit step function. It is a fairly simple function to understand. Not saying that to be rude or contrite. Does anybody have any questions about this bad boy before we move on to different things? All right. So the next function that we are interested in is the unit impulse function. Also known within math circles as the Dirac delta function. And mathematically, the Dirac delta function is defined as follows. So delta as a function of time is equal to 0 for all t that isn't 0, and it is equal to infinity at exactly t is equal to 0, where the integral from negative infinity to positive infinity of our delta function with respect to time is equal to 1. So it is an impulse of an infinite height and an infinitesimal width whose total area under the curve is equal to 1. So it's the unit impulse function because its area is equal to 1. So if I were to plot something like this, where this is my time axis, I would have it 0 until we hit t is equal to 0, and then I would represent an impulse as an arrow direction up at t is equal to 0, and then it immediately falls back down to 0 and stays at 0 forever. And I can also time shift my Dirac delta function as well. So if I had delta of t minus 3, that would just shift this guy 3 units to the right. Delta of t plus 2 would shift it 2 units to the left, and so on and so forth. So what do you guys think the relationship between the unit impulse function and the unit step function is, if any? So sounds like you guys maybe didn't learn this in Math 245.
It's been a long time.
It's been a long time. Okay.
I don't remember the second one, but I know the first one. But Lynn sometimes left stuff out.
Okay.
Yeah, we did. Some teachers can leave stuff out.
For sure, and I'm one of them.
Yeah.
All right, so let's think about things conceptually here, right? So I'm going to draw both of the functions next to each other, and let's see if we can sort something out. So on the left-hand side here, we'll have a unit step function. So that's something where we're at 0 until a point in time, and then we're at 1. And then over here, let's put our delta function. So this guy, just to recap, we're at 0 forever until we hit a specific point in time, t is equal to 0, and then we're at a value of 1 forever. For this guy, we're at 0 until we hit t is equal to 0, and we have an infinitely tall pulse, and then we're at 0 again. Amir, have you figured it out?
The Dirac delta function of unit step.
Exactly right. The Dirac delta function is just the derivative of the unit step function with respect to time. Okay. So 100%. So this unit step function, or excuse me, the Dirac delta function or the unit impulse function is a pretty interesting function when we think about things in terms of signal processing, because we can effectively decompose any signal that we could possibly come up with, generate whatever, as a sum of delta functions, because they only exist at one specific instant in time. So if we wanted a value of 5 at t is equal to 0, we would just have 5 delta of t. And if we wanted it to increase to 5.1 at t is equal to 0.0001, we would just add another delta function that gives us that, and we could construct any signal point by point by point. Okay. So that property is what's called the sifting property of the Dirac delta function. Okay. So if we have, let me come down here. Some function f of t multiplied by a delta function, and we take the integral of that with respect to time over some interval from a to b, then what we'll wind up getting is our function evaluated at exactly t is equal to 0. So let me just make sure that this makes sense to us. So this thing is 0 for all points in time except for t is equal to 0. So when we multiply these two together, at any time that isn't exactly t is equal to 0, the result is just 0. It only exists when t is equal to 0. So f at 0 gets sifted out of the signal. Okay. So this is true when a is less than 0 is less than b. We get 0 when a is less than b is less than 0, or 0 is less than a is less than b, so anywhere that isn't equal to 0 effectively. And then it happens to be undefined when a is equal to 0 or b is equal to 0. So if we let our limits of integration be exactly 0, we're just saying we're not super sure of what's happening, but we won't ever have a practical case like that. All right, so now let's get into some gross things. So we have this unit impulse function. Okay. So if we were to apply the unit impulse function to excite an electrical circuit, the response would be what's called the impulse response. Okay. So let's say that we have some linear time invariant continuous time system. Okay. So that's what LTIC stands for, linear time invariant continuous time system. So what this would represent would be literally any circuit made of resistors, capacitors, and inductors. Okay. Any circuit with fixed value components is an LTIC system. If we apply an input of a delta function, we get an output y of t that is h of t, where this h of t thing is what's known as the impulse response. And this is characteristic of the circuit itself. Okay? It is similar and in ways related to the natural response of a circuit that we talked about when we were doing transient analysis. By the way, our transient analysis was effectively what happens when we had a step function really at our input, and what we got out is that response, okay? So the impulse response is usually of a very similar form to the responses that we've already seen in our transient analysis in our previous classes and all that kind of good stuff. Okay, so let's take things a little bit further here. If I take that exact same LTIC system and I apply a time-shifted impulse function, where I'm shifting it by some arbitrary amount tau. So tau is just some amount of time, but I don't know what that amount of time is because it's a variable. Okay, so it could be 1 second, it could be 5 seconds. It's a parameter of what we're looking at. It should make sense to you all that our output should just be a time-shifted version of our impulse response. Okay, so that would just be h of t minus tau. Well, we know that for a linear system, I can scale my inputs because of that thing called the homogeneity property of linearity that I talked to you guys way back in Circuits 1. And so if I were to scale the input by some coefficient, x of tau. So just remember that tau is just some particular point in time. So x of tau is just a constant value, okay? So I've had x of tau multiplied by delta t minus tau. Then my output y of t should just be whatever I had here scaled by that same factor. So if I double the voltage as an input, I should get double the current as an output for an LTIC system, kind of thing. All right. So this is going to be x of tau times h of t minus tau. And now, if I integrate my scaled input such that I have the integral from negative infinity to positive infinity of x of tau delta t minus tau, what I should get is the integral of my prior output. So you guys will learn, oh, I need to squeeze in a d tau here. Let me move these over real quick. Because we need to know what we're integrating with respect to. Sorry, I lost my train of thought. Give me just a second. What was I talking about here? Oh, so I'm taking on faith here that you guys believe that integration is a linear operation. Now, we've actually used it as a linear operation every time we have effectively known the current flowing through an inductor, known the voltage drop across an inductor and found the current based on that, because that is an integral based relationship. Similarly, if we know the voltage drop across the capacitor, we can find if we know the current flowing through the capacitor, we can find the voltage using the integral. So we've used integrals as linear relationships previously. But I want to talk a little bit about what this thing right here represents, okay? So I'm performing this integral with respect to tau. So I'm letting tau just range from negative infinity to positive infinity. I'm multiplying this function x of tau by a Dirac delta function. So all this is doing is just taking a snapshot of whatever this function is over all different values of t and then adding them together. So this is just a way for me to represent my decomposed input signal as an integral or a sum of a whole bunch of delta functions added together and scaled by the function that I'm trying to model, okay? So this is just a really gross mathematical representation of any input signal I could ever imagine. And my output is the integral from negative infinity to infinity of that function multiplied by the unit impulse function with respect to time. So we call this integral right here a special name. This is what's known as a convolution integral. Okay. And so we can generalize things and say that for a linear time invariant system, if I have some input x of t as a function of time, the output of this linear time invariant system, y of t, will simply be my input x of t convolved with my input response, my impulse response, h of t. So this operation where we have an asterisk acting on two different time domain functions means perform this integral. Okay, that's just a shorthand notation. Isaiah, you had a question? So tau and time are both time. So I know that it's a weird thing, so we'll put this into practice here in a moment, and that'll help make sense of things. So convolution, I'm not going to lie, is not something that I am super comfortable with, but I bet I'm way more comfortable with it than you guys that have even had this before in your math 245 classes. So I'm going to try to explain this not from a math professor's perspective, because I don't really care why it works. I care how it works because I'm an engineer. I know that may be a cop-out, but that's the best that I can come up with. I'm not a mathematician. I know how to apply it. I'm not 100% sure on the why. Okay. So I want to talk about some properties of convolution so that we can know how things kind of work out. Okay. So the first property that we need to be made aware of is that convolution is commutative. Okay. So what that means is that F1 convolved with F2, actually let me use as a function of time here, is going to be equal to based on the definition of convolution that we have right up here, the integral from negative infinity to positive infinity of f1 of tau times f2 of t minus tau d tau. And this is the same as the integral from negative infinity to positive infinity of f1 of t minus tau times f2 of tau d tau, so that we can say that f1 convolved with f2 is the same as f2 convolved with f1. So the order doesn't matter.
So like you're essentially saying they're all the same thing.
So just like multiplication where 5 times 3 is equal to 3 times 5, the same thing applies to the convolution operation. Convolution is distributive. Meaning that if I have f1 of t convolved with the sum of f2 of t plus f3 of t, this is the exact same thing as f1 convolved with f2 plus f1 convolved with f3. It is associative. Meaning that f1 convolved with f2 convolved with f3 is the same thing as f1 convolved with f2, and then that resultant convolved with f3. And then we have our impulse property. This is a pretty handy one. So if I have a function of time and I convolve it with a unit impulse function, that returns my original function. There's also a property dealing with the width of a signal, but we're not really going to see that crop up at all in this class, so I will leave it to Dr. Amir to explain that one to you when you get to linear systems and signals next quarter, if he tends to give a shit about it. It's not a particularly important thing. Okay, so we have these properties, we have a definition. So now I want to make an observation about the world that we as electrical engineers live in that will help us simplify things slightly. I do mean slightly, but it is an important thing to note. How many of you guys know what the word causal means? So in the context of electrical engineering, a causal signal is a signal that does not exist until we turn it on, and then it exists. So effectively, our frame of reference is some point in time, which we commonly call t is equal to 0. And for all points in time before t is equal to 0, our signal can't have value. So it can't exist until we caused it to exist. Any physical system that we build will be a causal system because it cannot respond to a stimulus until we apply the stimulus, okay? So that means that in our definition of convolution that we have up here, all of this negative infinity garbage doesn't matter. We can start our integral at t is equal to 0 because we know all of our signals only exist for t greater than or equal to 0, and all of our responses only exist for t greater than or equal to 0. So in electrical engineering, our definition of convolution becomes y of t is equal to the integral from 0 to t of x of tau h of t minus tau d tau. And because we know about the, let's see up here, commutative property, we could also write this as the integral from 0 to t of x of t minus tau multiplied by h of tau d tau. So I'm pointing this out because we're going to be doing some weird mathematical substitutions and this, that, and the other as we learn how to apply this thing. And sometimes our input signal will be simple and our impulse response will be gross, and it might be easier if we did a substitution of t minus tau for our input signal as opposed to our impulse response. So it just lets us pick and choose how to apply the math to make things easier for us because we know it's going to get the same result either way. Okay. So we'll see that here in a moment. Another thing that I'm going to add here, and I'm going to wind up doing a little bit of hand waving when we work through a problem. So I should have some understanding that if the input of my signal, or my input signal is a causal signal, meaning it can't exist before I turn it on. And my response is causal, meaning that I can't observe anything until I apply an input. Then my output must also be a causal signal. So it doesn't turn on until t is equal to 0. So what I'm going to do here is I'm just going to sneak in a unit step function that kind of reminds me my output can't exist before time t is equal to 0. Okay. All right. So let's apply something here. Okay. So let's say sample number 1. That I have an input signal, x of t is equal to just a simple unit step function. And my impulse response, h of t, is given by the following expression. So I'll have a Dirac delta function plus something like e to the minus 2t plus e to the minus 3t u of t. For what it's worth, because you guys might think I'm literally just making shit up, this impulse response actually looks pretty similar to how things respond to being hit by an electromagnetic pulse. I use equations almost exactly like this, but these exponential scaling terms are much, much higher in my research for energy. Okay. So this looks like a bunch of mathematical gobbledygook, but it actually does represent real systems. Okay, so what we're going to do is we're going to try to figure out what y of t is if we know what our input signal is and we know what our impulse response is, right? So our goal here is to get some function in time. Okay. So I know that y of t is just going to be x of t convolved with h of t. But my h of t is kind of gross, so I can decompose it into three distinct impulse functions or impulse responses, right? So I might call this delta function here by itself h1 of t, and then e to the negative 2t times a unit step function. I could think of that as h2 of t, and e to the negative 3t times a unit step function could be a third impulse response. And so that lets me, this commutative property lets me split this thing up into three smaller convolution operations than one big one that would get real messy real fast. Okay. So I could have this as effectively x of t convolved with h1 of t plus x of t convolved with h2 of t plus x of t convolved with h3 of t, if that makes the math easier, and it turns out it very much will. Okay. So let's start figuring some stuff out, right? So I'm just gonna substitute things in here really quickly. So I would have u of t convolved with a delta function plus u of t convolved with e to the minus 2t times a step function plus u of t convolved with e to the minus 3t times a step function, like so. So we can already sort out one of these things. What's u of t convolved with a delta function? U of t, because of the impulse property of the convolution operation, right? So we're just going to start off knowing that one portion of our output response is going to involve a unit step function. Okay. Now we got to sort out the other stuff. Okay. So what I'm going to do is I'm just going to add an integral. So here's my integral from 0 to t, because my signal is causal and my impulse response is causal. So the limits of my integration only need to go from 0 to t. And now I'm just going to use my definition of my convolution integral, right? So x of t is just going to become u of tau. All I'm doing is just replacing the variable in my first function, or my input function, from t to tau. So I've got u of tau. Now I'm going to replace the variable of my impulse response function with t minus tau. So that's going to turn this e to the negative 2t u of t into e to the negative 2 t minus tau u of t minus tau. Sorry, that's right. I said t, or I said tau, and then I wrote it a t. So thank you for that. And now I'm doing my third guy over here. So that's going to be another integral from 0 to t of u of tau. And simply substituting in t minus tau everywhere I saw t previously, this will be -3 t minus tau u t minus tau d tau. So we have this big, ugly thing. Okay. So we're about to make some more simplifications. So let's think about things contextually here. Okay. I am integrating with respect to tau over some interval from 0 to t. So what is the value of my unit step function as a function of tau over this interval? So if I were to plot, I'm going to draw, let me go to like a couple of pages back from here. So here is tau. This is 0. So what I have drawn here is u of tau. Let's say that t is just some point in time as tau ranges from 0 to infinity. What is the value of this function, or any value of t between 0 and infinity? What? So, shit, I went too far. So this guy right here is just 1, and this guy right here is also just 1. Now let's sort out this guy. So I have u of t minus tau, where tau is my variable. Sorry. So this should look something like this. What is the value of this guy over the interval from 0 to t, or any value of t? Also 1. So all of my unit step function stuff just looks like the number 1 based on the limits of my integration. So I think I've made this much easier to approach mathematically now, because I've got the integrals of exponential functions, and I feel pretty strongly that I can do that damn near all day. Okay, so let's make our simplifications here. So we've got our u of t. We're going to have the integral from 0 to t of e to the -2 t minus tau d tau, plus the integral from 0 to t of e to the -3 t minus tau d tau. Okay, so I just got rid of all of these ones so things look a little bit cleaner. T is just some constant point in time, right? Just represents where I'm stopping my integration. So I could split these exponentials up into e to the -3t times e to the +3 tau. And I could do something similar for there. And because I'm integrating with respect to tau, the t terms can come outside. So that would look like u of t plus e to the -2t integral from 0 to t of e to the 2 tau d tau plus e to the minus 3t integral from 0 to t of e to the 3 tau d tau. Are we okay with that? So how do I take the integral of an exponential function? So the integral of e to the at is 1 over a e to the at, right? So this should look like u of t plus e to the negative 2t multiplied by 1/2 e to the 2 tau evaluated at t and 0 plus e to the minus 3t multiplied by 1/3 e to the 3 tau evaluated at t and 0. Are we okay with that? So now I'm just going to substitute those bounds in. So that's going to give me u of t plus so let's see here. So I'm going to have e to the minus 2t. This is going to be multiplied by 1/2 e to the positive 2t minus 1/2, right? Because e to the 0 is 1, so I have 1/2 times 1, so that's where that minus 1/2 term comes from. Be okay with that. Similar thing for my other one, so I'll have e to the minus 3t multiplied by 1/3 e to the positive 3t minus 1/3. And now I'm just going to effectively distribute things through. So I've got my u of t. What is e to the negative 2t times 1/2 e to the positive 2t? Just 1/2. And then I should have minus 1/2 e to the negative 2t. Similar thing here, this guy multiplied by this guy is just going to give me a factor of positive 1/3. Minus 1/3 e to the minus 3t. And now I'm going to do something that is going to seem a little odd. And this is where I don't have a really good explanation for the math behind it. But I have a really good intuitive explanation. I'm going to put brackets around this whole thing. And I'm just going to multiply through by a factor of u of t. I'm sure there's a mathematical reason that allows me to do this. But here's my logical reason that is allowing me to do this. I can't let any of these exist before t is equal to 0 because I have a causal system. So this is just forcing causality on that mathematical expression. Realistically, I could actually be multiplying it by the whole damn thing, but u of t times u of t is just u of t. So that lets me kind of factor out some things, right? So I have a 1 u of t plus a 1/2 u of t plus a 1/3 u of t. And then I have a minus 1/2 e to the negative 2t u of t and a minus 1/3 e to the minus 3t u of t. When I add 1 plus 1/2 plus 1/3, I get 11 over 6. And so this is just going to look like 11/6 minus 1/2 e to the negative 2t minus 1/3 e to the negative 3t, all multiplied by my unit step function. So that is what my response would be for this particular system. So let's look at something that's maybe a little bit more familiar to us. Okay. Yes.
Why did you put the T minus tau in the response function instead of the unit step function?
Maybe, I don't know. I just put it in my notes that way, so I did it that way. Best explanation I can give you.
So this answer is y of t.
Yes, this result here at the end is the y of t that we were looking for. So Isaiah had suggested that I could have put, instead of doing the t minus tau here, I could have just called this tau, this would have been tau, and put the t minus tau there. And it would have been easier. And looking at it, yeah, that seems pretty legit, actually. Seems like it would have made things way easier. But what's the fun in that? So, if anything, that proves that it doesn't matter what order you put them in, because you're going to wind up getting the exact same result, right? So this bit still would have canceled, this bit still would have canceled, and I just would have had the integral from 0 to t of e to the negative 2 tau, which would have given me a factor of e to the negative 2t minus 1/2, which is what this thing is already giving me anyway. And this guy right here would have given me a 1/3 e to the minus 3t minus 1/3, which is what this thing is giving me anyway. And I wouldn't have had to do this multiplication to wash those things out. It would have just fallen out naturally. So yeah, you're 100% right. If I had made a better choice for where I was substituting t minus tau and where I was substituting tau, it would have made this math easier. Very, very true. Okay, second example. Let's say that we have an input signal, x of t is equal to sine of 3t u of t, and an impulse response that is just e to the negative t u of t. So I say that this is familiar because an impulse response of just e to the negative t u of t, that's characteristic of literally a first order circuit. So an RL circuit or an RC circuit where our time constant was just 1. Okay. This sine of 3t u of t is similar, but distinctly not the same than the steady state sinusoidal analysis that we have done in the past, way back in circuits 1 and again in circuits 2. What's different? So when we were doing steady state sinusoidal analysis, our sinusoid existed for all time. So all the way from negative infinity at the creation of the universe to positive infinity at the heat death of the universe, right? That sinusoid always existed. Here, we're modeling a more real system where our sinusoidal function doesn't actually turn on until t is equal to 0. So what this is actually going to wind up giving us is not only our steady state response, but also the transient response built into a single package. And you'll see that we can very easily tell which part is our transient response and which part is our steady state response based on our prior knowledge of how a system like this should work. Okay? So if we're finding y of t again, so I chose, so let's see, y of t would be the integral from 0 to t. So I chose specifically here to make this guy where I'm substituting tau and this guy where I'm substituting t minus tau. So that's going to look like sine of 3 tau u of tau times e to the negative t minus tau u of t minus tau d tau. So what can we say about u of t over this interval? Still 1. What about u of t minus tau over this interval? Also still 1. So those unit step functions should go away practically every time. So I'm left with the integral from 0 to t of sine 3 tau e to the negative t minus tau d tau. So how, actually, we can go one step further here. I can separate my exponential and take the e to the minus t outside, giving me e to the minus t integral from 0 to t of sine of 3 tau e to the positive tau d tau. So how am I going to perform this integral? Integration by parts. You better believe it. Pretty much anytime we have a sinusoidal function, we're going to suffer through integration by parts. Okay. So just as a quick reminder, integration by parts tells us that the integral from 0 to t of u v prime, or dv, I guess would be a better way to put it. That might be what you're more familiar with, is equal to uv minus the integral from v, minus the integral of v du from 0 to t. And this guy is evaluated at 0 and t, if I'm remembering correctly. Okay, so what should be u and what should be dv? So exponential function should always be dv, right? Because that's the easiest thing. We can take the integral of it by looking at the damn thing, okay? So dv is just going to be e of tau, which by process of elimination means sine of 3 tau is u. So to get v, I integrate this thing, which, hey, it's just e to the tau, right? What's the derivative of sine of 3 tau? 3 cosine 3 tau, absolutely. Okay, so let's substitute things in. Okay. So this is going to look like e to the negative t multiplied by, so now I just take u times v, so that's sine 3t times e to the, or excuse me, sine 3 tau times e to the tau. So e to the tau sine 3 tau. I'm going to wind up evaluating this at t and 0, but I'm going to leave it in that form for now. And then I'm going to have minus the integral from 0 to t of v times du. So that's going to look like 3 e to the tau cosine 3t. Close my parentheses over here. How am I going to do this? Integration by parts, yet again. It's fun for the whole family. So in this case, I'm going to use a different color here. U is going to be 3 cosine 3t, which means du should be negative 9 sine 3. I kept saying t, but I meant tau. dv is once again going to be e to the tau, which means v is also e to the tau, right? So now I'm going to have this behemoth, e to the negative t, multiplied by e to the tau sine 3 tau, evaluated at t and 0, minus, open another bracket here. So 3 e to the tau cosine 3 tau, evaluated at t and 0, minus the integral from 0 to t of negative 9 e to the tau sine 3 tau d tau, close bracket, close bracket. So we can mess around with some things here really quickly. So for instance, this negative sign and this negative signs cancel each other out. So I can just call this guy plus and get rid of this guy. Then I can distribute this negative sign to here and to here to get rid of one of these sets of braces. So that would put a negative 3 there and then put a negative sign back here. And so we've got this thing. So remember briefly here that the left-hand side of this thing is y of t, which we found to be this integral. So I have an integral from 0 to t, or actually maybe a better way to put it would be this guy right here, right? So the left-hand side of this is equal to e to the negative t, integral from 0 to t of sine 3t e to the tau d tau. Well, I've got 9 of those right here. So I can just move these 9 over, giving me ten times the integral from 0 to t of e to the tau sine 3 tau. Actually, sorry, I've left off my e to the negative t, so I'm just going to put it back in real quick. I apologize. So 10 e to the negative t integral from 0 to t of e to the tau sine 3 tau d tau will be equal to this e to the negative tau times this bit right here minus e to the negative tau times this bit right here, right? So all I did was I just moved this thing over to the left-hand side and added it to the other integral of 0 to t e to the tau, blah, blah, blah. So I'm going to have e to the negative t, e to the tau, sine 3 tau evaluated at t and 0, and then minus 3 e to the negative t, e to the positive tau, cosine 3 tau evaluated at t and 0. I hear some whispering, so I feel like I lost you guys with one of my algebraic steps. Yes, Colton.
Where'd you get the 10 from?
Okay, so let me sort this out again. Okay. I'm going to take this part right here because I know that y of t is equal to this. I'm going to rewrite it right down here. Okay. E to the minus t integral from 0 to t of sine, actually, let me put it as e to the tau, sine 3 tau d tau. Okay. So equals this, still equal to that. Okay. I have minus 9 of that big ugly integral. So when I move it over to the other side, it gives me plus 10 of it.
Thank you.
Okay. So I've got this relationship now. I'm going to substitute in for t, substitute in t for tau and all of that kind of good stuff, right? So let's just look here. I've got 10 e to the negative t times the integral. Now I'm having difficulty following my own work. From 0 to t, e to the tau, sine 3 tau d tau will be equal to e to the minus t times, so let's see what I'm going to have here, okay? So when I substitute in t, I'm going to get e to the t sine of 3t. E to the t sine of 3t. When I substitute in 0, what's sine of 0?
1.
Sine of 0 is 0, which means I'm not going to have a second term. Okay. Then over here, I'm going to have 3 e to the minus t, and then I'll have e to the t cosine 3t. Maybe this will help really quickly. What happens when I substitute in my 0? I get e to the 0, which is 1, times the cosine of 0, which is 1. So I'm just going to put minus 1, like so. So from here, I can make a couple of observations, right? So this e to the negative t and this e to the t cancel each other out because I'm just multiplying them through. So my right-hand side of this thing is just going to look like sine of 3t minus 3 cosine of 3t plus 3. Are we okay with that? So e to the minus t cancels this e to the positive t here, which is why I don't have anything on this side. I'm going to distribute this e to the minus t throughout here. So e to the minus t times e to the positive t cancels out. So that's why I just have 3 times cosine. Negative sign comes from this guy. Then I have a factor of 3 e to the minus t times -1. That gives me plus 3, and then I need another e to the minus t up here. Are we okay?
Could you, use your red pen to cross this out too?
I don't want to cross those out because I don't want to imply that this doesn't get multiplied by that -1.
Okay.
Okay, I swear to God, we're almost done. So over on this left-hand side, I have 10 e to the -t integral 0 to t e to the tau sine of 3 tau d tau. So I could, if I were so inclined, move that factor of 10 from here to here. Are we okay with that? If I look back up here, I can see that y of t, what I'm looking for is e to the -t integral from 0 to t of sine of 3 tau e to the tau d tau, which means this thing right here is just the y of t that I was interested in, giving me the result y of t is equal to 1/10 sine of 3t minus 3/10 cosine of 3t plus 3/10 e to the -3t. And I'm going to tack on a u of t at the end because I know that this is supposed to be constant. We can go one step further here just really quickly, and I have to get out a calculator to do it.
Is it e to -3 at the end or just e to?
You're right, it's e to the -t. I just added that extra 3 in there because I'm a minute over and I'm trying to hurry through this. Can I add a cosine function and a sine function if they're at the same frequency? Absolutely. We did it in circuits 1, we've done it in circuits 2, and all of that kind of stuff, right? So using complex numbers, I could say that this is 3/10 angle 0. So 0.3 angle 0. Actually, that should be a negative sign because there's a negative out in front. So this is going to be 1/10 angle -90. 0.1 angle -90 minus 0.3 angle 0 gives me, screw you calculator, I don't want rectangular. .316 and some change cosine 3t minus 161.565 degrees plus 3/10 e to the -t, all multiplied by u of t. So which part is the steady state response and which part is the transient? Cosine is the steady state response. The exponential is the transient. Exactly like we would expect for an RL or an RC circuit. Excuse me. Okay, so on Friday, we're going to talk about graphical convolution. So doing this operation by flipping and sliding grabs and all that kind of stuff. And then we'll probably get around to starting our talk about the Laplace transform as well.